Good afternoon, everyone. Thank you very much for attending my presentation. In the next 15 minutes, I will be sharing with you this ArduWorm, a functional malware targeting Arduino devices. This is a proof of concept, and we will be talking about security, Arduino, and also the breaches of security in Arduino. I'd like to give you some context about our work. I come from the academia. I used to work at Carlos III University in Madrid, and now I am working at Cambridge University. This paper received an award for the best research paper, and it was an award given by INCIBE at a conference that was held in Malaga. So we did it together with a team of researchers from the Carlos III University. We did it with Jose Rodriguez, who was taking a master's course on cybersecurity, and now he works in Amazon in Dublin as a security engineer. And Alejandro Calleja, he is a PhD student at University Carlos III of Madrid. And myself, I am working as at Cambridge University. Well, first of all, I will start off with a brief introduction. We are all, I will tell you about Arduino, and more specifically Arduino June, which is the platform that we used for our research. And Arduino June will take us to the actual core of Arduino environment. That's where we have found the vulnerability that could lead to potential attacks. I will tell you about the security analysis that we did. As we said before, I come from the academia. I'm not a security auditor. When we do a security analysis, we play around with things, we take a look at how this works, and then when you find something, you say, this is possible that, well, perhaps someone may do a buffer overflow here, let us do it ourselves. But we do not carry out a comprehensive analysis. And well, some of you may believe that our security analysis is a bit shallow. So we, at the world of academia, we live on the publications that we make, and we did this research, and it is published. So now I'll tell you about the architecture used by Arduino, and this is where the greatest contribution of this work comes from. We have proven, we have evidence. Well, there were two research in this regard before, and we have gone beyond that, and we have proven that they are there. Arduino is working, very beautiful. You can do very many cool things there, but there is a problem there. It's not a problem that said, okay, I will be patching the software and the problem is resolved. It is a problem which is inherent to the architecture. It is embedded in the architecture. We will be going a bit lower down. We will be talking at the level of assembly. For those of you who are not that much into the technical side, so that you can follow it. And then also we use ArduWorm, and we created that piece of malware. It is not working. We have the source code, open source, available so that you can download it if you so wish. And then also briefly, if I have time, I hope I will have time at the end of my presentation, I will share with you a solution to this problem. It is AV RAND. It has been discussed in previous talks. It is kind of like ALSR, and we are proposing it for our situation, for our paper now. We are starting with introduction now. Today, in the previous presentation by Nico, we've seen that we have hooligans at home, Russian hooligans. They have gone into our home. We just gave them internet access, meaning that anyone can access in your home. So the Internet of the Things embraces all these devices, smart devices, because now everything is smart, and we are less and less smart, so to speak. So everything is smart, our refrigerator, and then a door, so that my cat walks in and out. So there is an endless number of possibilities, and I'm all the time, when I'm talking about the Internet of the Things. I have to say that the Internet of the Things is extremely useful in industrial projects. The Internet of the Things help us out, but the problem is that there are several security failures, and sometimes these devices are off-the-shelf devices. That is to say, you buy them, you take them home, you install them. Well, I have my baby monitor. I know nothing as to how to set up a system. I just bought it, I downloaded the app, and now I can monitor my baby with this camera. This is very good because it's a plug-in, no configuration whatsoever. But if you are using this default configuration, you are just more vulnerable. And why is this more important? Well, it is important because many times these devices are present in critical scenarios. If we are talking about temperature regulator, well, perhaps it is about regulating your home temperature. And but what happens if that device regulates the air conditioning? If the air conditioning doesn't work, that could be a huge problem. And sometimes these devices are used in medical devices. What happens if I have a pacemaker, electronic one, and then it is connected through RFDI or through Wi-Fi? And if I need emergency surgery, then it is switched off. So, well, imagine if there is someone controlling my pacemaker and that person is ill-intended. So imagine what happens. There are other devices that are connected to the internet, and you may go and say, well, who is interested in controlling my home refrigerator? But someone may decide to attack it, and then so that I lose all the food is ruined. However, this can be used for denial of service attacks. This has been mentioned here. This is a recent attack that has been quite discussed in the media, and it is the Mirai botnet. Well, it has been proven that the denial of service attack that was took place in the 21st of October, and actually, well, system Verizon, Amazon were impacted by it. And then you may wonder how this could happen. Well, the thing is that they attacked the DNS that these companies used. It was well thought, but actually what it used underline was a vulnerability of user and password by default, and they used the default username and password that came with the device. And that's why it is important to protect these systems. What are the challenges that we face? Well, these devices sometimes are limited in resources. The most best example is the battery. Well, the protection that you implement cannot take up or consume more battery than the actual device. So we have to be very careful, and these mechanisms have to be energy or low consumption in terms of energy. And that's a challenge for researchers and for academia. And also we have to remember that attackers can analyze our systems. Sometimes our systems are deployed in open places, so sometimes the camera that I have here can be sold is sold at any supermarket. We should not forget that the attacker may get the binary, analyze the architecture, and then once he's got that information, go ahead and attack our system. As I say, our paper is based on Arduino. It is used on the a lot in the for the Internet of the Things because it allows you to do many things. For instance, there is a drone, Arduino-based drone, another one to produce your own glove. There are very many tutorials on the internet, and so okay, you buy Arduino, then this chip, and then you can configure it. This architecture, perhaps it is not very much used for industrial processes because IRM has is much more advanced, has taken over ABR. However, this system is so easy of use, and and so cheap that it's being used quite a lot for a small project. And relatively short ago, well, people said, no, there is no malware for Arduino. Arduino is safe. The problem with Arduino is that Arduino is so basic, so lightweight, so light that it is very complicated to organize attacks, to structure an attack. You cannot really make or implement very sophisticated attacks, and then you may go and say that defending yourself is also difficult, but it is defending yourself, protecting yourself is not as difficult, and I will tell you more about it. So Arduino June is a platform for open source electronic projects, both software and hardware. This is ease of use. In case of Arduino June, it also embeds internet connectivity. Arduino is made up of a microchip, a microcontroller, AVR. In the case of Arduino June, we are talking about 80 Mega 3204, and that's where you can plug in the several gadgets, a sensor, or a Wi-Fi card, or a Bluetooth antenna, you name it, you decide on it, that goes to Arduino, then you do your Arduino program software, and then it controls everything. You program it on C, and that's it. It is up and running. And many people were demanding that, and many people were demanding that Wi-Fi cards. And then Arduino June decided to offer that. They said, okay, in the very same chip, in the same device, we are going to offer the two chips. One which is a microcontroller, the typical one, as well as a microprocessor, AC2, which is quite light, but with a bigger capacity. With more capabilities, and it is also runs under Linux. You have Linux peripherals, Ethernet cards, with Wi-Fi cards, USB connection, USB port. So it is kind of like small computer. It's a microprocessor. So these two chips, both the Arduino microcontroller as well as the Linux microcontroller, are controlled by a serious port hardware, and it is there. You cannot use it for anything else, and it is also connected through a software known as Bridge. Bridge, we will talk about it more later on. It is the critical component. This is the one that we have used for our Arduino. So now moving on to Arduino, and I'm going to go deeper and deeper, going down and down. So we analyzed the architecture, which is AVR. This architecture, well, I'm sure that you're aware of x86, IRM, and this is a different one. It is based on Harvard. It's Harvard-based architecture. Those of you that study IT engineering, you know that this is the Newman architecture that we are taught at university. This is a different paradigm, architecture. It divides or separates flash memory from RAM memory. Physically speaking, both these memories are separated. The flash memory, that's where all the code is stored, and that's the coding that will be executed. And it also has a bootloader. That memory cannot be written or read. You can only execute it, and you can only load it from the bootloader. When you want to flash out a new program, when you want to install a new program, you do it through the bootloader. So in Serious Programmer, and then you plug in your program, the bootloader writes it, and then it goes right away to the start. And every time you restart the device, the first thing that is executed is the bootloader. And then in the case of the RAM memory, it has the code, the data, a heap stack, and you hear it is not executable. It can only read or write. This is, as has been said here this morning, this is data execution prevention measure. That is to say, you cannot inject your code there and execute it at the same time, because you either write on it or you either execute. You cannot do both. And this is a physical thing. There is no operating system saying that this page can be read or not. This is a physical thing. Therefore, with this, you are preventing code injection attacks. However, this is not a problem for hackers, and what we use here is the reuse code attacks. And here we have lack of memory controls. There is no operating system. Then when there is a memory overflow, then there is timer in hardware, which is a watchdog. And when the code stays there in the device, the only thing that you can do is to restart the device. This is what Microsoft decided to do when you used to get that blue screen. Okay, you restart and that's it, you fix it. And then also important from the viewpoint, well, this is important for you to understand what I will tell you about defense. Well, the memory is organized in pages, the same as in other memories, and then the program counter does not point right away to the instruction that you want to run, but the page that you want to run. And then within the page, there is a part that points at the page, and then there are some small elements that point to the offset on the page. And I'm telling you that so that you can follow what we did in terms of our defense, because for defense, we decided to move pages. So this way of arranging the AVR was very good, was very helpful for us to design our defense system. So here we have the OpenWRT. This is Linux. This is Linux distribution for embedded devices, light ones, router. There is a specific version, OpenWRT June. I have to tell you that all the research that we did and led to all that started last year in December. And we said, okay, let us take this OpenWRT and analyze it. And the version that we have now was released on May 2016. It came with a number of changes that I will tell you about later on. You know that, well, you may have some added capacities or features here in OpenWRT Young. And this is a critical component. And here there is an only user, and then the default password is Arduino. So then you have some elements to start playing around with. So this is what we did in the beginning. This is the start of our security analysis. If I buy an Arduino Uno and I want to use it to control my garage door or whatever from my mobile, is it secure? Can we really trust Arduino Uno? As everyone says in the forum, Arduino is secure. Well, we know that the Linux part is not, the Linux side is not secure. So we started to analyze it like anyone would analyze it, someone with some knowledge of security. I would take a look at the maps, ports. I would do like a black box analysis. And then we went into the shell and we started to play around with it to see how bridge worked, operated, and then we moved into the Arduino environments. And I said, well, the university, they did not explain anything to me about this, so we decided to go through the explicit specification to understand how it operates it and to understand it. And also this bridge library, we looked at how it is implemented. Bridge runs under Linux. And this Arduino also has an API which is quite large, has many libraries. That library is implemented under C. And we said, we can do many things with the memory. We started to play around with it. We did some proof of concept, and this is, the result of that proof of concept. This paper that I'm presenting with you. Well, the version that was released in May 2016 started in 2014. There were lots of security failures. The drop bear SSH was vulnerable, and when in the user registration. So these are security failures that had not been patched. You could also have remote command execution because there was a vulnerability on BusyBox for Linux commands. And now this is the name of the paper that has just been released. And then when we did bridge analysis, I said, okay, we will take Python, we will analyze, we will see how it works. We started to understand the communication protocol. It goes through the serial port. And then we said, who executes, who runs the bridge? There is no user, you execute it under root. Then there is a process which is running, and it is executed under root. And then the commands that I get through Arduino, I run it, and I run it with the user permits as a user, a super user. And then if we manage to exploit the Arduino part, well, let us do whatever we want to do, of course, with the permits of super user. And then we went into the AVR, where I will be repeating some of the things that I told you before. There is a flash memory, and this division, division, the code and data. So this cannot, you cannot do code injection into it. And then bridge, as I said before, it is a library under C. And in Arduino and AVR, there is no module for dynamic load of module. So there is no component for you to load the modules dynamically. So when you do double click and you run binary code, then it is loaded in the library. All the libraries that you point out get that uploading, and that's where you do the ALSR. So here there is no module load. When you compile it, you compile the program, which is under C, you compile it with a compiler, and you link it with all the libraries that it will be using. That's binary code that goes to the flash memory, and then it is executed. Libraries are there. We could see that the bridge library has a function. When you import bridge for whatever reason, the whole library is imported. And that's why we have this function that we like, the run shell command, that it receives a pointer to the Linux commands that you want to execute. So for instance, a Sketch, a small Arduino program, can execute a command in the Linux shell. So we have more things now for our work, and because you cannot inject code, well, a technique that I liked but I'd never used before was the ROP and the return to lib. And then I said, okay, let us do these two things. So AVR exploitation. I will go deeper and deeper. Now I will tell you about the assembler, and I will tell you how these ROPs work. And well, I believe that was mentioned this morning, but I will tell you more about it, and I will tell you what we do with it. And the idea is the following. If I cannot inject code, I will be using whatever is available. I know that there are binaries, there are programs that are running in the memory, and that the code is there, can be executed. Otherwise, it would not be running. However, I cannot introduce my program, my shell code, because I cannot really write on the memory and execute at the same time. Data execution prevention measures, well, the only are there, so therefore the attacker, the only thing that he can do is reusing existing code. So therefore, I know that the libc execute v function is there. I'm going to call it for it to be executed. Well, the first thing that an attacker has to do is to kidnap the execution flow of the program, because the program is being executed on a number of instructions, whether it is a loop or a condition. It goes from one place to another, but it is designed for that. And then when the attacker says, okay, the next command will be the command that I will give you, and then I can tell the program to execute for me whatever I want it to execute for me. And that's where the magic is. What do I want to do? Well, the simplest thing for me to say is I want you to execute the function of this library, exec VE. And then that function is waiting for you to send out a parameter, because the function wants to execute. In PCs, in x86, you can do it through the battery. So you control the battery, you give it to it, and that's it. And that was the simplest way to do it. However, what happens if you want to do something that it is not implemented or embedded in a library function? And that's where we have this magic here, which is the return-oriented programming. And you go and say, okay, you will be executing a bit here, another bit there. So you are kind of chaining gadgets, which are small fragments of code, that is to say, small instructions that are executed sequentially in a manner that at the end, when I have the full sequence, they do for me whatever I want them to do for me. The name given to them is return-oriented programming. I'm talking about it, and here it is based on all these code fragments. They all have to end up in a return, and that's what I said on the screen. On the screen it says for any assembly languages, they all have different functions. The recall or call functions. Whenever a program is being executed, I want to execute a function or a method that is somewhere else, and I call it. I call it to that address. I call that function, I call that address. Whenever that function is executed, it has to return. And how do I know? How is that information transferred? That information is communicated or transferred through the stack. And then it says to the call, okay, by the time you finish, you come back here. Then that function is executed, and then the return says, where do I have to come back? Okay, from the stack, I take the memory address that I was given, and this is the next thing that I'm going to execute. Then it comes to the flow, and everything works all right. And now we take for granted that if an attacker can control the stack, therefore can change that return value, and therefore kidnap the flow. Therefore, how can we chain different gadgets? So the attacker goes and says, okay, what you have to do next is to execute this. But when you finish, you go and I will point at a different place. And when you finish, I will point at a different place. So therefore, in the stack, different pointers are introduced as well as the information that is necessary, because sometimes the code consumes and writes data on the stack. You really need to know how the program works, but you can go and say, okay, when you finish executing this, you go and execute this for me, and then everything is changed into this longer sequence. And this is what we did.
Bueno, pues objetivo principal, ejecutar un comando en el OpenWRT.
Okay, main objective. It's execute commands in OpenWRT-UN. This receives a pointer to the commands that you want to execute. And how do you transfer that in AVR? Here we use registers. When you are executing a function, say, okay, for instance, this function, I have to execute this command. Where is it? Well, whenever I'm told that it is. In this case, register 24 and 25. Therefore, you load the address that you want to execute, you load them on registers 24 and 24, and then you call to that function run shell command. It knows internally that the command that you want to execute, it is in register 24 and 25. What do you have to do? First, hijack the control flow. Then you have to prepare the command, that is to say, you write on the memory the command that you want to be executed. That is a Linux command. In our case, we download a script and we execute it, wget or you name it. Then that command, that string has to be written on the memory. And then I prepare the arguments and go and say, well, okay, register 24 and 25, point to that command there, and then I jump right away to the function, and that's it. And we just let it go. And well, the issue of writing on the memory is a bit more complex. We have published that in our paper. Of course, it is open source. You have more information on the paper for those of you who want to go into greater detail.
So that you understand what I mean, we have the memory command already written, and so what can we do next? This is a stack overflow, the typical one that is used in the overflow. This is a call, this is a function that I called vulnerable function, right? So when you call this function there, the return address, DVE, is stuck on top of the stack. So we run this function that first brings together several records. This is called prologue and epilogue. And it helps us because it's using the records. So what we had is stored with the stack. I do what I need and I rescue it later. So it all works normal. We see how records pile up. We can have a buffer, you've seen this 1,000 times, that is declared as a local variable. We keep some space for it on top of the pile or the stack. It's from 0 to the buffer size limit. Vulnerability happens when the buffer is filled in a vulnerable way, when limits are not controlled. This is a typical buffer overflow. So the premise is the AVR chip gets data from the serial port and Bluetooth. As long as we have data available, we keep them on buffer. And no need to have a condition that it's and it should not be bigger than buffer size. As long as there is a space, it's okay. So we guess there is a buffer overflow vulnerability. In practice, we've seen in our world, it tends to be the case. If this is possible, we can have padding, we can crash down anything we want, remove everything we want. And when we want to go somewhere, that the attacker can choose where to leap to. So what we chain together is, this is a vulnerable function. So when it comes back, when it is returned, the attacker gives us a gadget address. It is a code fragment that we found somewhere in the binary code. So we guess that the attacker has access to the binary code to look into it. So we have a pop out 25 and 24, and there is a perfect return because it takes from the stock values, records them into 24 and 25, and gives me a return. So 24, 25, I say. This is a pointer on the command that I've written somewhere. This is done by the exploit, but I haven't explained it yet. And so I send the pointer to the command that it's out there, and so when you run a return, I send you the memory address where ransom command is. This gadget here, the first one run with this little pointer, takes the pointer from the stack to the stream that I want, to the commands I want, and this return tries to find what to execute next. Next would be ransom command that is run. It's kind of a small gadget that on the paper we called the argument, load argument. There are some gadgets such as save this, reset chip. You've got some more details on our paper. This is a diagram where we can inject a command onto the memory before running it all. What you need to consider, and I've explained it already, because of the AVR design, the stack is always on the highest position growing downwards. An attacker could never set all pointers from all gadgets. So if you ever had a tutorial, or you're familiar with it, when you have a ROP attack on a PC x86 or IRM, which is quite fashionable lately, what you send is lots of pointers, and you need to take back from the stack. This is a large pile, and you take it from the pile and you run out of memory fast. Here it's even faster because the stack starts at the lowest position, so your payload is limited by the amount that the stack pointer has gone up. So we've tried the typical Arduino tests, and most of the time you don't have a chance to a larger payload. How do you change this with ArduWorm? Since every time you have one of these payloads, you are ruining the stack, the device. What happens is it is run, it's executed as you want, but it is crashed. It is a blue screen. So you got the timer kicking in and resetting the device, and it all starts anew. So new attack, new exploit, another payload, reset, and we automated it in a Python-based program through Bluetooth, sending an exploit, waiting a bit for that to reset, and then sending a new exploit back and a command sequence to have it executed, and so little by little. And that's why we've got a gadget that is called chip reset. So run and reset, run and reset, run and reset. Since it's all go back and starts anew, the program ends up working. This is the adversary model. We didn't make it up. It's not our invention. We understand that an attacker cannot do it all on one move, because if you can, Arduinos are open, so go for it. It is complicated. But if you do it little by little, you can achieve things. This is AVR exploit stage, and I would like to prove that you can attack on Arduino devices. Anyone having an AVR chip, all Arduinos have one, well, and other systems as well, because AVR is not very common, but it's used widely though. And so any device that has AVR is vulnerable to this kind of attacks. We've used UN, and why is that? Because it has the breach and has also internet connectivity, that helps us with the malware part. The idea is that any library using Arduino can be exploited by an attacker using reuse code. So if you've got a device that it's online, or you've got Arduino June, it makes no sense that a sketch running on Arduino wouldn't implement the branch functions to use Linux. And so that's what we thought. We thought that this would be a device where as the CCTV camera could be connected, then the sketch would have some kind of library or firmware to control said camera. If you manage to use the firmware following code reusing techniques, you can do anything you want. What we want here is to use Linux. What did we do? So this is ArduWorm. This is a command. It doesn't work. This was done locally, but still, you download the program. I say it's costly, but this command takes some 10-12 seconds. Sends and resets. It might be 12 seconds, which is quite enough. But we don't say run this and then that. Our proposal is download this worm and we will place it onto Linux, and from there onwards it's under control. What does the worm do? First installs a payload, a RUT, because it's a proof of concept to prove everything that can be done. Actually, anything that you can come up with user permission if connected to the internet, if you're online. Send the password and everything. Actually, we use this because we had the master's degree. We were studying master's degree and we thought this could be interesting. I was teaching malware analysis and engineering, so I said, do whatever you want, do malware engineering. So I sent out the password file to our server. That would not go into John the Ripper, but it would be no cracking. Just wait a bit and get a dictionary in return to then spread. A rat was installed, that it was Python implemented, and then surrounding recognition. See what I have. Ports 22 and 23 are open. You can do anything you want with active interfaces, fingerprinting of the operating system. Now we can only use the Linux version because, yes, of course, with the Windows device we got a few things, but it would also look for additional serial ports. And what's that? It could be that there is one open port because there is Bluetooth, the device is connected, and through the serial port, the attack that I explained, the return-oriented programming exploit works through the serial port. So Arduino takes data from the serial port. If you've ever used Arduino, it's easy to connect it. You can have a serial port that it's adapted to the USB, and there are different options. We were using the Bluetooth this time around. So it's a serial port connection to other devices, and that's where we crashed the ARV down. That's the way to spread it. I have no video or anything of the kind. We just tested it in the lab. We had 2 Arduinos, had fun, and we could see how it would spread automatically. But this is not just a malware saying it has an impact on operating system or a program, but there is not a given program. When you buy Arduino, you need to install the program yourself. So if you've seen, we can hack Arduino, and you can understand that the attacker can do the same thing a user could. At persistence as always. Run at start and open additional ports just in case, to escape firewalls, etc. Potential implementation scenarios. There is this interesting paper that is enemy at home. Your enemy's at home. I don't really recall how it was, but there is this virus for a Google thermostat saying that if you manage to do this, when you get the update, there was other kind of malware on the IoT, and this is our proposal. You've got an Arduino on your local network, and it has a Bluetooth, for example, so that when you get home, you can upload it, or it's connected in any other way that can be exploited by an attacker. Once they manage, they're in to your home network. If you, well, that would be home-based, but maybe if you dare use Arduino at a company, it would be the same. Also, the sensor networks. There are some tutorials open so people can build up their own sensor networks to control, same as with any other sensor network. Once you've got one, you can spread it, and we always understand this is online. Naturally, we see that internet connectivity is used by ArduWorm to spread. But I guess that anything that you do with Arduino, temperature at home or fridge, then, or a cat access, or anything like that. So this is a specific now. We tried it out, and we had a few projects, we implemented them, so it is not just our proof of concept, but we also have an attack against this project here. Well, we didn't find it, but do not underestimate it, because an attacker who's willing to do so will. Before conclusions, in the sector of cybersecurity and cyber research, we always need to make proposals. This is the breach, this is the bug, this is the problem, but we need to go further. How can it be solved? Basically, what we did was, how can we use this code reusing attacks for x86 or similar structures, or ARM? That is a hot topic. Often, there are many conferences taking papers on this. How is it done? Two options. Let me explain first the one we didn't use, that is control flow integrity. That would be controlling the integrity of the flow. So, if you could see, okay, because it's jumping up and down, how is it not more than 8 or 10 instructions run consecutively, or why is it this library and then the next? You can have some control and understand what your program flow should be like, so that when something is leaping and bumping and something is being run that is not allowed, it's all about controlling integrity. And these are the techniques most used now. They are the hottest, and we have hardware support actually available now. x86 and ARM. This shows promise, but it takes lots of resources. So whenever I run something, I send a pointer somewhere and change somewhere, there is another instruction that needs to be run to control it, another routine. For AVR, we found it was way too complicated. Flash memory was only 32K, so it's complicated. The other option would be ASLR. This is code reuse technique, where the attacker knows where what they want to run is. I know where the ransom command is, where the gadgets I want to take are, so I get my exploit ready, and I say here, there, and over there. What if it doesn't know where? We will make sure the attacker won't find out how. We will upload code in different memory addresses every time. This is what ASLR does. And it is a technique where whenever a library is uploaded, it is done so in a different memory address. Problem with ASLR is that when you upload a whole library, you can have memory address liquids. Leaks, rather. So we can find where the memory address is. So if the attacker managed to know where the pointer is run, where the instruction is executed within the library, I know that within the whole library is at a given offset. So I just need to recalculate my ROP, my exploit, based on what I got here. So I will not give you an exploit with the static addresses anymore, but first thing I do is get the memory address, and from there onward I know where the whole module has been uploaded, and since it's a full load, what about a kernel 32DLL library? It is so big and gets so many gadgets in there, I can do anything I want. So they are very sophisticated attacks, quite interesting. You can try them out using just-in-time compilers. ROP attacks, just-in-time ROP attacks. So this is all about chasing, and we took over this idea. Let's randomize the memory space. And so what we do is similar to ASLR, but granularity goes up. So this is just a binary, so up or down, not much more to do. But what we do is redistribute every page. So the memory is paged, and what we do is redistribute page numbers. There were some technical challenges and it was complicated. So whenever you move a page around, all pointers move around, because if I call a function when it is moved around, this all changes. And there's a paper, I will show it later to you, the reference I mean, to the paper, in case you're interested in more details. I don't have the time now, it could take me 20 minutes to explain it. And we don't have an operating system uploading modules when the user clicks there. So first thing run is the bootloader, which is a loader, and that's for the boot time. And these randomizing machine and logics are implemented on 4 keys available for the bootloader. So it was complex, and we've used the RAM on C function. We cannot use a ransom twister. It would be too complex and it doesn't fit in. It was lightweight, but it works. So someone might come and say, this is an exploit that will crash your thing, and that's great. That's how learning works. But so far we find it is a solution that in the cost-benefit ratio is good. It's only about software. There's no need for extra hardware. This is the source code and you can implement it if you wish. This works on binary code. This is Intel X format. We have a preprocessed module that is run beforehand on a computer, and it takes information on where every pointer, every function is, because that will be necessary later on. So there is a preprocessing module that gathers some metadata. Some of those can be public, so the attacker can know about them, and others we guess they should know, because that's where each web page number is. The program needs to know where the pages are. If page 1 used to be 000 and now is elsewhere, there's some point where I need to know where it is to undo it later on, to re-randomize it all. These are known as private metadata. I use XOR to encrypt it. Please do not kill me. It's what you need, an XOR key that it's also stored and move around to prevent the attacker from gaining access. With bootloader, we have some kind of metamorphism. It is self-encrypted, so there is a non-encrypted part that encrypts all the re-randomization part. It runs, randomizes, and reruns and stores. It's 4Ks, but if the code is left free, non-encrypted, it could be used by the attacker and can write on the memory, because, well, this is not something that it's protecting. And we protect it with a short XOR with a key, and so the attacker finds it a bit more complicated. I have lots of slides on how it works later on, but I will not explain it. I'm around, and you have also details on the paper. Conclusions. Arduino is great. If you like playing around, it is great to learn how to do things, but be careful. There is no security measures. It's not just a vulnerable program that can be patched. It is just an architectural failure itself, and there's nothing that can be done. And even though this is not a contribution that will change the world, but it's good to know that someone's taking the time to put forward few solutions. We think AV Run helps the Arduino community to show it. It's randomized, it's tested, and I think it takes 1.5 seconds for libraries. 1.5, 1.8, that's overhead time, not much. Only if you reset the device. But if there's someone trying to attack on us, playing around with our device and resetting all the time, at least with every reset, I change it. I treat you, and you cannot move on. What we do not learn is that we need to patch everything. We cannot have the same distribution from 2014 to 2016 with so many vulnerabilities. If I buy an Arduino, you can do it yourself, but some people don't know about it. These are off-the-shelf products, as I said before. This has been it for me. If you have questions, remarks, great. These are the links. They're gone now. But we have the ArduWorm code also available on JIT, and also information on VRAM. Find me on Google or wherever you want.